Okay, here we're looking at a Rankine cycle, okay, and this is ideal, so it's all reversible, everything like that. So coming into the turbine, I've got 1600 psi, 1100 Fahrenheit. The condenser pressure is 2 psi, so pressure 2, pressure 3, 3 psi. By definition, what comes out of the condenser is saturated liquid, so the quality at state 3 is 0. Okay, basically I want to find the power, the total power, and the efficiency. So again, the first step I'm going to want to do is set my states, which is look up H values. Now, I can easily look up H1 and H3 because I have two properties. Any two properties set my states, right? Got pressure, temperature, pressure, quality right here. Okay, now going from 1 to 2, I recognize again this is an ideal Rankine cycle, so everything is isentropic. Therefore, if it's isentropic, the turbine is isentropic. Not everything is isentropic, but the turbine and the pump are isentropic. Okay, so if the turbine's isentropic, that means basically S1 equals S2. I can look up S1, right, because I know state 1, and I know then S2 equals S1. Once I have P2 and S2, I can then look up H2 in the table, right? Because any two properties set my state. Okay. The pump we do a little different. Remember, the pump is a liquid, steady state flow through incompressible substance. So again, we're going to use that the work of that pump is VdP, right? V times the change in pressure. Okay. And that work is also going to equal delta H. Okay, so what do I do with that? Okay, well, I'm going to need the volume. And again, the volume will more or less remain constant because it's a liquid. It's incompressible. Okay, the pressure through the boiler is constant. So P4 equals 1100. So now I have, P3 and P4. I'll know V. Okay, and then knowing that the work is V times delta P, it also is delta H, so I will be able to calculate my H values here, thus setting all of my states. Okay, so let's go through. We'll start at state 1 here, okay? And I'll look up state 1 and state 3 since I can look those up directly. So I'll start with the 1100 degrees, 1600 psi. So I'm right here, 1600 psi, 1100 degrees. I have an H value of 1547 and an S value of 1.6315. Okay. Coming out of the condenser, remember I'm at 1 psi. So I go to saturation for water, 1 psi, and my enthalpy is 69.74. And again, my volume that I'm going to need is 0.01614. Okay, so let me go ahead and jot these guys down. So again, H1 was 1547.7. S1 was 1.6315. Okay, that means S2 is also 1.6315. Moving on to state 3. State 3, this is 69.74. V3 was 0.01614. Okay, so now I've set state 1, state 3. Now I can do state 2, which is 1 psi, and 1.6315. I can look up my H value from these. So I'm going to go back into my table. At 1 psi, you can see that my entropy for saturation is between 0.13 and 1.97. The fact that I'm at 1.63 means that I'm halfway in between these two. Well, not halfway. I'm somewhere in between these two. That means I'm somewhere in between on the enthalpy as well. So I do, I can find the quality and whatnot, and calculate my enthalpy is going to be somewhere between 69 and 1105. Again, probably much closer to the 1105. When I do the interpolation from these, I get 911.2. And again, that's because I'm partway in between saturated liquid, saturated vapor at state 2. Okay. Again, knowing that I'm at this pressure and this entropy, I can do interpolation to find where I am for enthalpy. Okay. Now, over here at state 4, again, excuse me, what I know is that the work of the pump is basically V delta P, and it's also the change in enthalpy, H3 minus H4. So again, I know everything here. I know V, I know my P's, I know H3. The only thing I don't know here is H4, but I can solve that and find that H4 equals 74.52. So again, we use this idea of the isentropic steady state flow of an incompressible substance to find the work of the pump, both using V delta P as well as delta H. That helps me set my state, which is what I'm looking for. Okay. Now, knowing the mass flow, I can now find the power developed, which again is just going to be the turbine minus the pump. So again, once I set my states, I basically just go through and calculate what I'm trying to find. So the work of the cycle is going to be the mass flow times H1 minus H2. That's the turbine, minus the pump, which is H4 minus H3, right? This is work out, this is work in, this is the mass flow rate. I will let you do the calculation yourself, and I get the work of the cycle equals 8.84 times 10 to the 8th BTUs per hour. My thermal efficiency, again, is going to be the work of the cycle over Q in, which is going to be the work of the cycle, which I just calculated, divided by the mass flow rate of what comes into the boiler, which is just going to be H1 minus H4. Again, knowing those H values, I can just plug them in here and find my thermal efficiency to be about 43%. So again, the process is exactly the same. Go through, set your states. I knew state 1, state 3. I use constant entropy to figure out state 2. I use what I know about the work of a pump to find state 4. And once I find those, it's just a lot of delta H's to find the work and the thermal efficiency from there.